Good morning, and welcome to our event. My name is William Malik. Thank you very much for your time and attention during this session. What we're going to be doing today is discussing building the cyber resilient smart city. In order to do that, we're going to begin by defining what makes a city smart, and then we'll take a look at some of the vulnerabilities that smart city architectures and designs confront us with. We'll drill down in detail into a couple of them. We'll look at some issues associated with 5G, and we'll take a look at some problems associated with Internet of Things generally. We'll conclude by looking at some techniques to remediate, to minimize the consequences of these vulnerabilities, and then we'll have time for questions afterwards. So thank you very much, and let us begin. So we're going to begin by defining what the cyber resilient smart city looks like. We'll take a look at the components, the architecture, and the vulnerabilities of this environment. In 2014, the government of Scotland put together a report on smart cities, and they defined a smart city as one which used data and digital technologies to provide sustainability, citizen well-being, and economic development. I believe this is an excellent place to start, and so we'll be operating on that. The two main points are that it is good for the people and it is good for the business the people will be doing in that environment. Now let's take a look at some of the architectures that we see in smart cities. There are many. This one is not chosen because it is particularly better, but it distinguishes itself through the amount of detail and the explanation of the interconnections. This is from Alibaba's ET City Brain. Look at it, alibabacloud.com to get more information on it. What we see here is a multi-layered approach with sensors and real-time data, along with historical data being analyzed at the lowest level, particularly focusing in this instance on travel, transportation, intelligence transport systems. But as we bubble up through the layers, we begin to see more sophistication and intelligence placed in the process. Now, in some cases, this is human intelligence, people making decisions. In other cases, as the technology is deemed worthwhile, we'll actually see decisions being made by this technology. This, of course, is a careful process. This is not something you rush into. The vast amount of storage and connectivity that are necessary for this, and the vast numbers of sensors of all ages. We're not just looking at brand new technology. One of the challenges of smart cities is that much of the infrastructure has been in place for a long, long time. The tunnels providing fresh water to New York City were dug in the late 19th century. So we're looking at structures that are a century and a quarter old, or in some cases older. And these are controlled by devices which have been put in place more recently, and sensors overlay on top of that. So maintenance and just awareness of the performance of the components of the city are an important part of maintaining the integrity of the smart city. Now, note that the goals of a smart city are no different from the goals of any city. What we're doing to make it smart is we're going to use electronic technology, both in the forms of big data and in the forms of machine learning, to augment the capabilities that the managers would normally put in place to keep things running smoothly. Now let's take a look at some of the areas of vulnerability in smart city architectures. Unfortunately, there are many. This chart, which is taken from a report by the School of Science at Edith Cowan University in Perth 3 years ago, takes a look at the components of a smart city and identifies some of the areas that could be attacked by hackers. The smart grid, for instance, presents a problem because it depends on information coming from smart meters in order to do things like precisely control load. Unfortunately, most smart meters are not particularly hacker-proof, and we have seen projects that show that a distributed attack against smart meters could corrupt them, leading them to generate false indications of load. Now, the problem is that if a bunch of meters say they demand power, then what ends up happening is the smart grid will seek out and contract for additional electric power to be delivered to that city. However, if the load doesn't actually materialize, if the demand was spurious, then you have a problem of what to do with all of this load plus the economic cost of the misleading information, of the misleading indications of demand. Smart cars, another area of significant vulnerability. Automobile manufacturers are trending in the right direction, including better capabilities for security and integration. But at their heart, automotive networks, that is the thing inside the car, are flat. There are many of them, but they communicate freely among each other. And the devices, as in all automobile manufacturing, are as inexpensive and as lightweight as possible. Inexpensive, simple, and lightweight does not admit for much security. There's very little security available to these. Some vendors have made available software development kits that will allow auto manufacturers to put security, particularly in the in-vehicle infotainment system. Now, what this does is that serves as the port, both for the broadcast of your GPS data, handling your stereo, setting up a local Wi-Fi hotspot, enabling Bluetooth communications and so on, but it's also the input to the car, not just for gestures and taps on the screen, but verbal commands. And more importantly, you can introduce devices such as USB sticks or content from your smartphone, which will then flow into the automotive system and have access to everything. A few years ago, one automobile manufacturer was caught out by allowing a USB stick to be played if it had a file called update.exe. Without any checking, without any date validation, without any security, without even so much as looking at the size of the thing, if a USB stick was put into the car and it had a file called update.exe, that automobile manufacturer would run that file. And the system underneath the infotainment was Windows 7 and did not present a great, formidable challenge to any would-be hacker. In addition to what goes on within the cars communicate with other cars for efficient travel, and they also communicate with infrastructure to handle such things as sudden changes in demand on the roadway, say a traffic jam, or the need for emergency services to get through to particular areas. For these reasons, smart cars, while a component, are also vulnerable. As we go through the list, just about every component in the smart city itself is at risk. And we will do our best to describe what kinds of remediation can happen. Before I move on, I want to talk a bit about smart buildings. This is particularly interesting. A smart building system controls all of the activity within the building by monitoring key parameters throughout. So for instance, if an escalator breaks, it will tell the smart city system that it is no longer functional. This is a medium security incident. Here's why. If an escalator breaks, it comes to a stop smoothly and it does not throw people around. And when it's stopped, it's locked in place. So while it's still not escalating, it serves as a stairway. So it's a medium level incident. Nobody was probably harmed or injured. And you can still walk up and down the stairs, although it wouldn't be your choice. So therefore, with a medium security incident, you dispatch a repair crew to block the thing until it can be fixed. Now, if an elevator gets stuck, that is a high severity incident because there might be people trapped in the elevator, and it would be a significant inconvenience as well as a risk to the security and even-mindedness of the passengers if they can't get out. So if an elevator comes to a stop, we need to get a crew there right away. Now, understand again, the engineering behind these devices is such that you're not likely to drop an elevator. That hasn't happened in decades. But you do want to get the people out and put the thing out of service and get it fixed as quickly as possible. At the bottom end of the scale, if the system hears glass breaking, that would be a low severity incident. You're going to have to dispatch a janitor, a custodian with a mop and a bucket to pick up whatever liquid's been spilled and dispose of any broken glass or ceramic. So that would be low severity, unless the smart building is connected to the public safety system of the smart city. And the public safety system is reporting that there is an active shooter incident in that vicinity, in which case that broken glass could be an indication that there is a bullet that's penetrated the wall of the building and therefore it needs to be evacuated. Where does information security come into this equation? You have to be able to trust that traffic. You have to be able to trust the message. You have to have the sender and the receiver authenticate mutually. The receiver has to know and be able to verify that the contents of the message have not been changed. You don't want to suppress a message with such information, and you don't want to react to a forged message pretending to provide such information. So these are the kinds of vulnerabilities. Now, underneath all of this is the rapid communication between components, and that's provided by the 5G network of the near future. We'll next talk a couple of charts on where 5G is and where it's going. This is the timeline as of March of this year for 5G. What we're looking at here is the series of releases. Now, understand that 5G isn't one thing. It's actually a series of 4 releases. There was some groundwork put in release 14. Most of that became 4G LTE when the magnitude of the 5G issue became clear. And so much of 5G is in releases 15, 16, 17, and 18. So where are we with release 16? 15 is done. 16 is going to be completed this year, but understand at the time this chart was developed, we hadn't yet fully understood the implications of the current pandemic. Therefore, that's going to slip. Now, the head of the group working on release 17 has said that he wants to minimize the content of release 17. He only wants 12 or 14 or 15 features in order to keep the length of time of the release down to a year or 15 months at the most. So release 17 will not be available. It started work this year, will not be available until 2022. If you're a manufacturer, you can't begin building something that is compliant to a specification until a specification is published, which means that the release 17 specification, which will be published towards the end of 2021, will be the starting gun for the development of 5G compliant handsets in tune with release 17. And release 18 follows that. Now let's take a look at what's in release 17. The important point here is not to identify and go through each of these. The point here is just to take a look at the number of items that are candidates for release 17. Much of this has to do with new radio. This is the higher frequency stuff. This is the stuff that is going to be carrying the traffic that is going to enable smart cities. And as I said, the leader of this group only intends to allow 12 or 14 or 15 of these items, which means the remainder, all of which are submitted by the manufacturers that have a stake in 5G, the remainder will then have to be resubmitted as candidates for release 18. Release 18 isn't going to kick off until next year. And since it's going to be a big release, that'll be a 2-year cycle. So we don't expect the specification for release 18, which will contain the bulk of what's left for 5G. The specification will not be done until late 2023. Do not expect to see full function 5G handsets in the market until 2024. So there's time to prepare for this. Let's take a look at some vulnerabilities associated with 5G. Basically, it's end-to-end. The first point is it will rely heavily on virtualization in order to handle the vast number of requests. The increasing density of the devices means we need many more antennas. That means the antennas will be inexpensive. A couple of years ago at Black Hat, some hackers showed how they could create a fake 5G and 4G antenna for less than $1,000. The retail price of a 5G antenna will be about $250, about 200 euros. So it'll be easy to forge them at the front end. And as I said, at the back end, the virtualization both of the network and of the application stack will require a tremendous amount of sophistication and efficient and high performance productivity from the infrastructure. That adds up to vulnerabilities as a consequence of the complexity. So we expect 5G to have a range of problems which will not be addressed quickly. And again, remember the spec isn't done for another couple years. In the IoT area, this is just a list of some of the companies that recently reported that they had been using the VxWorks stack. This is a common shared piece of code, which includes the TCP/IP stack. Rather than write your own, you just pull it down from the appropriate shared library. In the digital version of this presentation, those underscored components in red are actual links to the pages from these vendors explaining what to do to handle those vulnerabilities. These have been around for 13 years. The defects in this code were published in 2007, and they're still being discovered today. Urgent 11 came out late last year, and there was a more recent one that just occurred a couple of months later. What can we do about it? Well, we need to take a look at the technology, and we need to take a look at our interdependencies. Last April, we had a significant issue when the global positioning satellite system had a partial failure. The reason was that the GPS satellites count the number of weeks from the beginning of time in order to figure out where they are. They know how fast they've been moving. If they know when they started, then they can calculate where they are. And the way they calculate the amount of time since the beginning of time is they click off the weeks since January of 1980. The earlier satellites used a 10-bit counter. Now, if you get a 10-bit counter, the biggest number you can deal with is 1023, and then you roll over. There are 52 weeks in a year. That means less than after 20 years, these satellites rolled over. It happened in August of 1999, but nobody cared because GPS satellites were not heavily integrated into technology. When it happened last April, we saw a couple of interesting consequences. Fortunately, none were life-threatening. Aircraft, in fact, the latest 787s from Boeing, began reporting that the date was August 22nd of 1999. This is a screenshot from a Air China 787 showing that today's date is quite a few years ago. With a problem like that, the manufacturer has to then ask the component manufacturer, what's going on and can you fix it? And the component manufacturer didn't know what was going on. They were getting their time signal from the older satellites. On the right, we see a picture of a device the New York City police use to see if you're speeding and then check the license plate and bounce that off a database. Well, the problem with that system was it relies on the New York City Wireless Information Network, NYC-WIN, which also depends on time signals from the satellite, which also crashed on April 6th, 2019, and it was down for 10 days. This isn't a code defect. It isn't the result of a hack. It's an architectural decision that was made over 30 years ago that led us to put satellites in place with an architectural vulnerability that didn't have consequences until last year. The solution was to roll the dates forward. You can't go into a satellite and change the hardware. So they still have 10-bit counters, which means in the year 2038, we're going to go through this again. Another area that was a more significant kind of failure for smart cities was the Sidewalk Labs, that's a division of Google, plans for Toronto's Quayside. This was a 100+ acre area that Google was going to essentially make as smart as it could by monitoring everything. The project was canceled because the citizens believed that they would not have their privacy rights protected. And Canada has a much broader regime for protecting personal information than the US does. This cancellation was a significant problem. Hundreds of millions of dollars had been invested already. And the result is a failure of public trust led to the cancellation of a project. So what do we do about it? Well, Civic information security, bring people in, let them understand what's going on. This is a system that's up in Rhode Island. If you're in Rhode Island in the United States and you dial 311, you'll be put in touch with a bank of, uh, call them level one tech support for the entire state, where you will get an answer concerning any probable cyber attack against your machine. You don't have to be a student, a business person, a registered taxpayer. If you're in Rhode Island and you can dial 311, you'll get to their information system that will provide this. The benefits of this are, first of all, it gives students who are answering the phones work experience in handling cybersecurity. Second, it gets people, any kind of people, retirees, students, business people, folks at home, some level of assurance that if they have a problem, it will be addressed. And thirdly, it gives the state information about any kind of ongoing cyber attack. It strengthens civic participation. So, what do we do to preserve the smart city? If you're an administrator, make sure that what you do preserves privacy. Make sure that you test and continue to test after deployment. Set up a cert and make sure those systems will be around a long, long time. You're going to have to come up with accelerated mechanisms for patching these systems. You're going to have to come up with fail-safe techniques. What about vendors? Vendors should provide encrypted and authentication communications technology. You got to be able to prove you are who you say you are, and what you said was what you actually intended to say. More and more vendors are setting up bug bounty programs. These reward the individuals who find defects. This is, in fact, a more efficient way from the vendor's perspective than running penetration tests. You basically are crowdsourcing the discovery of vulnerabilities. In all cases, remember the escalator. That is, allow for manual override in the event of a failure. Design for fault tolerance and make sure that whatever happens, you are able to continue to provide necessary services. That brings me to the end of my prepared remarks. I mentioned some references. There are more in the handout associated with this. And now I'd like to take your questions. Thank you for your time and attention.